All right, let's talk about graphing when it comes to simple harmonic motion. So looking at position time graphs, velocity time graphs, acceleration time graphs, and even the energy graphs. Now, let's say for instance, we've got this top view of a mass that's bobbing on a spring, right? And if you're taking paper notes, I would highly recommend you getting this figure out of the notes and putting it in your paper notes for future reference, especially when we come to the conceptual questions, because this is a really good um, visual as far as what all of your graphs look like. But so if we're looking at this, represents the top view of a mass bobbing on a spring on a frictionless table, right? So this right here, the yellow or the y equals 0 line, that's your equilibrium position. So what they've done is they've displaced that mass, right, some distance a, your amplitude, your positive amplitude, and they release it. Well, what happens? The restoring force of the spring pushes it back towards equilibrium. It goes to a negative amplitude, the maximum displacement off of your equilibrium position, and then it gets pulled back in past equilibrium and then back towards your positive amplitude. And so this cycle repeats itself over and over and over again. Now, if we're looking at graphing the position versus time here, at time equals 0, you're located at your positive greatest displacement, your positive amplitude. Right, so he's starting here. Now notice our times are all going to be in terms of the period. This representing one full period of motion, right? One full cycle of simple harmonic motion. So at time equals 0, you're starting at your maximum positive amplitude. At 1/4 of your period, you've reached equilibrium, right? So it goes down to equilibrium, and then by the half period, he's halfway through his cycle, right? Which means that he's at the maximum negative distance, right? The negative amplitude, right? Represented down here. Then it's pulled back up by the spring, back to equilibrium position at time equals 3/4 period. And finally, at time equals the full period, he's reached the positive amplitude again, right? So you have it's starting from maximum positive displacement going through equilibrium to maximum negative displacement through equilibrium again back to maximum positive displacement. So the position time graphs are easy enough to read as long as you're really looking at this y-axis, right? This represents your maximum positive displacement. This represents your maximum negative displacement. And in the zero is always your equilibrium position. Now let's translate that into a velocity time graph. Well, think about what's happening here. What's the velocity here at time equals 0? Well, it's 0, right? You have pure spring potential energy. You have no kinetic energy. As it comes down, you gain kinetic energy. You have maximum kinetic energy here at the equilibrium position. Then you have pure potential energy here at your negative amplitude, which gets converted back to pure kinetic energy here at equilibrium, which gets converted again back to pure potential, right? So it's the same thing as looking at a pendulum swinging back and forth, right? At either extreme of that pendulum swing, it's got pure potential energy, right? Which is not moving, right? But at the bottom of that swing, right there at equilibrium position, all of that potential energy has become kinetic, right? And so that's where your maximum velocity is. So if we're looking at translating your position versus time graph to a velocity versus time graph, well, we know that at the amplitudes, its velocity is 0, right? So we look down here, corresponding amplitude, 0 meters per second. Negative amplitude, 0 meters per second. Positive amplitude again, 0 meters per second. Now, where is velocity greatest? Again, when it passes through equilibrium, when all of that energy has become kinetic energy, right? So at position 0, you have full velocity. At position 0, you have full velocity, right? And you got to look at what direction it's moving. So in this case, notice that If this is our positive direction and this is our negative direction, this is moving from positive and it's moving in the negative direction towards negative a, right? Which means that its velocity is in the negative direction, which is why you have this negative velocity peaking here, right? As it's pulled back up, it's moving towards the positive position, so your velocity becomes positive and peaks at equilibrium position here. So you really got to look at or imagine when you're thinking about your position versus time graph, what direction it's moving in. And that's going to define how you sketch your velocity time graph. Now, moving towards your acceleration graph, notice that we have maximum accelerations when we're at our amplitudes. And the reason for that is because at these amplitudes, it's changing direction, right? So that change in direction represents your maximum acceleration, right? So here at positive A position, it's changing direction, so maximum acceleration. Here at negative amplitude, you've got change in direction, so maximum acceleration. And again here at positive amplitude. Now, why is the acceleration 0 at your equilibrium positions? Well, the reason for that is that if you look at the net force acting here, well, you've got a spring force. Spring force here, the spring force is 0 because the spring is not neither compressed nor stretched, right? So if you look at that, if your net force is 0 and your net force is that spring force, well, 0 equals mass times acceleration, therefore acceleration has to equal 0. So your acceleration is maximum when it's changing directions, and at the equilibrium positions, your acceleration is 0. Now let's talk about direction here. Why is the acceleration negative between the amplitude and your equilibrium position? Well, it's negative because it's speeding up in the negative direction, right? Or if you just look at the picture, right, it's speeding up right here in the negative direction, downwards. Now, then, after it passes equilibrium, your acceleration is positive. Well, why is that? Once it passes equilibrium, the spring is going to start to pull on the mass again, which is going to slow it down, right? Meaning that the acceleration is directed in the positive, right? If it's moving in the negative and slowing down, you have positive acceleration. Now, here, again, you still have positive acceleration because the spring is speeding it up back towards equilibrium, and it's moving in the positive and it's speeding up, so you have positive acceleration. Once it passes equilibrium, the spring is becoming compressed and it's going to start to push against that mass, right? And so it's moving in the positive direction but slowing down, meaning that that acceleration becomes negative. Right? So you really got to think hard about what's really happening in terms of the motion here. But again, this is an excellent cheat sheet. And we'll get a lot of practice with this here soon. But let's take a look at what energy looks like on a graph for a simple harmonic motion. Now, here we have the same scenario, just viewed from the side, right? You've got your mass that's bobbing on the spring between some negative amplitude and some positive amplitude. Now, in the pink, we've got kinetic energy. In the blue, we've got potential. And in the red, we've got total mechanical energy, right? The sum of your potential and kinetic. Now, notice, energy is conserved, right? Your total mechanical energy does not change. But what does change is the amount of potential and the amount of kinetic energy. So, if we look at it, at each one of your amplitudes, your kinetic energy is 0. Well, why is that? Because at your amplitudes, the block's not moving. Now, at equilibrium, where all of that potential energy stored within the spring has become kinetic energy, your velocity is maximum, right? And your kinetic energy is maximum. So you have this move from no kinetic energy to gaining, gaining, gaining pure kinetic energy at equilibrium, losing kinetic energy until you have zero kinetic energy at your amplitude. Now, your potential energy, in this case, the spring potential energy, right, is maximum when the spring is most compressed or most stretched. So that's at either one of these amplitudes, negative x and positive x. So your spring potential energy is maximum at the amplitude, decreases until it's zero at equilibrium, right? When your spring is in its equilibrium state, it's neither stretched nor compressed. And then it decreases until it's zero at until it's maximum at your amplitude, right? And so you have this cycle of your potential becoming kinetic, kinetic becoming potential, but your total mechanical energy remains the same, right? So if we were to look at that in more than one back and forth motion, right, what you'd have is the solid line is your potential, the dotted is your kinetic, and then the solid is your total mechanical energy, right? Again, your total mechanical energy does not change, but your potential energy your potential energy, the solid line, drops and rises and drops and rises as its position changes. And the same thing with your kinetic energy. So just looking at this with no perspective as to what the object is doing, you can tell, well, when potential energy is maximum, so here, 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 and here, we know that it's at its amplitudes, right? It's either at positive A or negative A. When kinetic energy is maximum, so here, 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 and here, or sorry, and let me back that up. Let's start again on this graph. All right, so when your potential energies are maximum, so here, here, and here, we know that it's at its amplitudes, whether it's positive or negative amplitude. When your kinetic energy is maximum, so here and here, we know that it's hit equilibrium position, right? So down here, this represents zero, right? So kinetic energy is zero here at the amplitude, it's zero here at the amplitude, and it's zero here at the amplitude. Your potential is zero here at equilibrium and zero here at equilibrium. Now notice your energy is not going to fall below the x-axis, right? The energy is always going to be a positive value here, right? Because when you're looking at your energy, well, kinetic energy, right, is 1/2 mv squared. So no matter what direction it's moving, it's positive. Your potential energy is 1/2 kx squared, right? So no matter what position it is, it's positive. So your energy is always going to be above the zero, your x-axis, right? And so where it's maximum is going to tell you whether it's at the amplitude or whether it's at the equilibrium position, depending on, whether you're looking at kinetic energy or potential energy. So what I would recommend is take a hard, long look at this diagram here. It's very helpful. Study it. Think about what's happening here, what's happening here, why is this happening here, and why is this happening here. But let's take a look at stop to think 14.3. So the graphs in the table above apply to pendulum motion as well as motion of a spring on a mass. A pendulum in a clock has a period of 2 seconds. You pull the pendulum to the right, a positive displacement, and let it go. We call this time t equals 0. We want to know at what time will the pendulum A first be at its maximum negative displacement, B first have its maximum speed, and C first have its maximum positive velocity, and D first have its maximum positive acceleration. So pause the video here, take a second, think about these answers, see if you can use this graph above you to help you out. All right, so it might help to sketch out what you got. You've got a pendulum, right, where this would be its equilibrium position, 0, right, and you pull it to the right for some maximum amplitude, positive A. And it's going to swing through equilibrium to negative A back through equilibrium to positive A, and continue to repeat that process. Now, we know the period is 2 seconds here. So we know that to go from here to here takes 1 second. To go from here to there and back to here takes 2 seconds. So if we're looking for when it's going to be at its maximum negative displacement, well, its maximum negative displacement is your negative amplitude, right? So it's going to take 1 second to get to its maximum negative displacement. Now part B is trying to trick you a little bit. They're asking you when will it have its first maximum speed. Speed meaning we don't care about direction. So if we're looking for when it's going to have its first maximum speed, it's going to be when it first hits equilibrium. So if we're dropping it from here and it takes 1 second to go to there, we know that this is going to take 0.5 seconds for it to hit equilibrium. So at half of a second, it reaches its first maximum speed. Now C is asking for when it will have its first maximum positive velocity, meaning that it's going to have to be traveling in the positive direction, so towards positive amplitude. So it would have to be at equilibrium and traveling this direction. So it would take 1 second and a half, so 1.5 seconds would be its first maximum positive velocity. And lastly, when would it have its first maximum positive acceleration? Well, remember, your maximum accelerations are at your amplitudes when it's changing directions. So where is it going to be accelerating towards the positive? Well, here when it's at negative A and it's changing directions into the positive direction. So that'd be time equals 1 second. So now let's take a look at example 14.2, motion of a glider on a spring. An air track glider oscillates horizontally on a spring at a frequency of 0.5 hertz. Suppose the glider is pulled to the right of its equilibrium position by 12 centimeters and then released. Where will the glider be 1 second after its release? What is its velocity at this point? So take a second, pause the video, see if you can't figure that out. Alright, so again, it always helps to sketch out your scenario. So in this case, if this is our equilibrium point, and this is an overhead view, we've taken that glider and we pulled it back by 0.12 meters. And then we release it, and it's going to oscillate back and forth between a negative amplitude of 0.12 meters and a positive amplitude of 0.12 meters. Now we're also given that the frequency is 0.5 hertz. Right, so if period is 1 over frequency, well, 1 over 0.5 gives you a period of 2 seconds. So we know that every 2 seconds it goes there and back again, which means that at 1 second, its position is at equilibrium. So if we want to find the velocity at this point, well, we can use conservation of energy, right? Where your initial total mechanical equals your final. Well, initially here, we'll call this position 1, and we'll call this position 2. At position 1, you have pure spring potential energy. At position 2, you've got kinetic. So 1/2 kx squared equals 1/2 mv squared. So if we were to solve for v, you'd get kx squared over m and square root. Now, obviously we don't have enough information here to solve out for v, but that's where the equations that I'm going to introduce in the next video will come in handy. These equations will allow you to solve for maximum speeds, which this would be your maximum speed given your frequency and your amplitude. So we'll cover those new equations here next video. But for now, remember there's a daily problem dealing with an experiment involving a pendulum that is going to be due Friday at midnight. And yeah, just again, make sure you thoroughly look this over and see if you can't, imagine these graphs in your head and then look back at this. But yeah, I'll see you in the live sessions.